we looked at augmented matrices.
Yes, okay. So I think we solved the system like this, where matrix A, this matrix A was a square matrix, right? And on the right-hand side, we had some vector B. And what was the way in which we viewed this system? What is it that geometrically that we're thinking about? What's going on when we say 1, 2, 3, 4, X, and my X vector is X1, X2 equals, I don't know, 7, 8. What is it that we're talking about here?
The idea that the matrix C times a certain vector is another vector.
Yeah.
Yeah.
So yeah, essentially. But what you said is we took this preferred way of viewing this as what linear combination of the vectors of the column vectors of A. So x1 and x2 are some numbers, some weights, some real numbers, and they could be complex, by the way. I don't know why we're talking about real numbers. It's because most people are used to deal with real numbers. But x1, x2, some numbers. So what combination of these vectors, the vectors being 1, 3, and 2, 4, when I weigh them and add them up, will lead me to the vector B, which B is this vector here, 7, 8. Okay, 7, 8. Okay, and we saw that in some, it may be possible, it may not be possible, but in the examples that we had, I think it was the example where it was possible. Okay, so now today, again, last time, the matrices were and by the way, we want to investigate conditions under which it's possible and under which it's not possible. That's where we're headed, essentially. But last time, our matrices, our A, were square matrices, or either 3 by 3 or 2 by 2, but they were square matrices. Today, we want to do two things. First, we want to extend our conversation to matrices that are not necessarily square. They would be M by N matrices, where M and N are not necessarily the same. So for example, you would have a 3 by 4 matrix of rows, 3 rows with 4 entries each. Okay. And those would be applied to vectors, and out will come some other vectors. Now, please help me out with this before we move on. Now, if I have a 3 by 4 matrix, what kind of vector is it applied to? So let me take this 1, 2, 2, 4, 3, 8, 6, 16. Let's take that just a random matrix. It's a 2 by 2, 2 by 4 matrix. Could have written down a 3 by 4 matrix, but it's a 2 by 4. So it's applied to what kind of vectors? So this is, again, so remember, our matrices, we think about matrices, they're stand-ins for linear transformations. Okay, then what's a linear transformation? Okay, we gave some definition of what it is. But roughly we're thinking that this is a function that's applied to vectors of certain dimensions, and on the other side, outcome vectors of another dimension. So what is the dimensionality of the vector to which this matrix can be applied? What is the dimensionality of a vector to which this matrix can be applied? So it can be applied to a bunch of vectors, but all those vectors have a certain dimensionality. What is that?
The 4 by 2?
Yeah, sorry?
4 by...
You can multiply it by 4 by 2 matrix. That would be defined, but we're applying it this to vectors. Yeah. So, but you're correct. It would be a 4 by 1 vector, right? So this is a vector that lives in the 4-dimensional space. So something like that. So let's call it x1, x2, x3, x4. And outcomes what? What dimensionality?
2 by 1.
It's a 2 by 1 vector. So let's call it b1, b2 to be consistent with the notation ax equals b. Okay. So this A here, this A, let's use this color because this A is a function from the 4-dimensional space to a 2-dimensional space. Do people agree? So last time, when we dealt by 2 by 2 matrices, those were transformations from R2 to R2. Okay, we could have drawn these vectors, the input space vectors in the 2-dimensional space, and out came 2-dimensional vectors. This time, 4-dimensional vectors go in, because I have a 2 by 4 matrix, and out come 2-dimensional vectors on the other end. Okay, so that's happening. This our matrix, our transformation is from R4 to R2. Now, if I have 4 variables, and I'm only constraining them, all 4 of them, with just 2 equations, chances are that I will get some freedom of choice in what values to assign to the variable. So first of all, I'm going to have some solutions, right? I'm going to have some solutions That is like I know this is all vague. Now we're going to make this very precise in a minute. Not in a minute maybe, but in a few minutes. But if I have just one constraint, like let me pick an example. Let me pick a very simple example that I will post later today. 3, 2, 1 multiplied. What's the solution to this? By some vector equals a 0 vector. Okay, so let's have this aside, and I will erase this later. This is my matrix A, which is a 1x3 matrix, essentially. Okay, it's applied to 3-dimensional vectors and outcome 1-dimensional vectors. Those people who have had linear algebra, by the way, what did you call this multiplication? When you this way of multiplying two vectors where the outcome is just a number. So you have when you multiply, so that you're essentially multiplying a row vector to.
I kind of forget. Is it the inner product?
Yeah, that's the dot product. Sometimes it's called or an inner product. Yes. Yeah. So this product. Okay, fine. Let's forget about it. So this is A. I use blue here. A is a 3x1 matrix that's applied. Oh, I'm sorry, 1x3 matrix that's applied to a vector that is 3x1, and out comes a single number. Now, for values x1, x2, and x3, I can. So what is the solution to this? So there's one obvious solution, but there are others. Actually, let's pick something that's even simpler. I don't know why I picked 3, 2, 1. How about you pick 1, 1, 1? How about 1, 2, 1? I don't know, whatever. Like, I don't know, maybe I shouldn't have even changed it. Like anything, just some 3 numbers. What is a solution to this?
0, 0, 0.
That always will be a solution. That always will. But this one, the point I'm trying to make here is quite subtle.
1, 1 minus 1, 1.
Okay, so there is a non-zero solution, and that's the point I'm trying to make. Yes, whatever you named was a solution. I'll write it down in a second. But let's draw for a second an analogy with just the real numbers. With the real numbers, just the first time you saw numbers, whenever it was. So you multiplied 8, when you solved the equation, like in school, ax equals b. So for example, 5 times x equals, I don't know, 1, or let's say equals 0. What's the solution to this?
0.
Yeah. And by the way, is this the only solution?
Yes.
Yeah, it's the only solution. 5 times x. So you cannot multiply 5 by a non-zero number and get a 0, right? So that's the only solution. Not so in the matrices. So these are completely different objects that we're talking about. We're saying that I can take a non-zero vector, non-zero matrix. So 1, 2, 1 is a non-zero matrix. This guy is a non-zero matrix. We'll see that this one times x equals b will equal 0. So that's what we'll be solving, called a homogeneous system of equations. It's more about the terminology later. For now, what matters is that we're taking some non-zero matrix times a vector, and out comes a 0 vector. And the solution to this is something non-zero. That is, as you've just suggested, if I take this non-zero A and apply it, I think you suggested 1, 0, minus 1. Is that what you suggested?
I said 1 minus 1, 1.
Okay, 1 minus 1. Okay, 1 minus 1, 1. That's another one, by the way.
Or minus 1, 1, minus 1. It's 1.
Okay, so there are a bunch of others, right? The point is that on the other end comes out a 0, no matter what non-zero solution. So here's a good example. This A is not 0. This vector V is not 0. But you apply this non-zero A to non-zero vector V, and out comes Zippo, a 0. This is what cannot happen in the field of real numbers. So here are your real numbers. And this 5 times x equals 0 has a unique solution, x equals 0, right? There's no way to get a non-zero x here to make 5 times that x a 0, the 0. There's 1 0. Okay. So again, so we're dealing with these objects like this. So by the way, the vector to which you apply a and get 0 on the other end is said to be in the null space of A. So for example, this vector 1, 1, 1, this vector V equals 1, 1, 1, rather 1 minus 1, 1, is in the null space null space of A. That is, there's some non-zero thing to which when A is applied, you'll get a null, you'll get a 0 on the other end. Solving a system of homogeneous equations. Now, what is homogeneous is just a fancy way of saying that I'm solving not A equals B, but AX equals 0 is what I'm solving now. So A in this case is a 2x4 matrix. I'm applying it to a 4-dimensional vector. Out comes this time a 2-dimensional 0 vector. So I'm going to have a 0, 0 on the other end when I apply it. And I want to know what's in the null space of A. So solving a homogeneous system of equations corresponds to determining what is in the null space of A. Now, if this were a linear algebra class proper, I would define this null space. It's kind of clear now what it is, but we would prove a bunch of properties about the null space. For example, we would prove that null space forms a vector space, for example, among other properties of the null space and so on. But we're not going to do it in this class. We're just simply going to go ahead and see if we can find an algorithm, which we actually started talking about last time, called Gauss-Jordan elimination, which finds out what the null space is, which computes the null space for you. So we should be able to write down exactly which vectors are being transformed by this matrix A to a 0 vector. So let's do that. So I'm going to insert a page after this, and let's just get started. So everybody's on the same page, like what it is that we're doing. We want to determine what's in the null space of this linear transformation. Is a good way of thinking about it, but the previous, like high school way of thinking about it, maybe just solve for me a system of linear equations, AX equals 0, right? Same thing. We apply, so this is our A. So we apply Gaussian elimination. So the process will be this. We start out with this A, and it may be like 20 by 70, this matrix, but in our first example, it's like a 2x4 matrix. And we will reduce it to what's called a step-like matrix, or an echelon form of a matrix. Row echelon form of a matrix. A row echelon form looks like this. This is what we mean by a row echelon form of a matrix. So echelon, okay, so step form, okay, like step-like form. Okay, what's step-like form? So you have some non-zero entry here, and below it you have a bunch of zeros that came up last time already. Okay, and we'll end up calling these guys that sit at the leading entries at the steps that are sitting like at the corners of the steps are called pivots. We'll call them pivots. Okay, we'll make a big deal out of them in a minute. And the other guys we'll call free variables. But that's coming in a minute. Just wanted to give you a heads up what we'll call things. But for now, we want to reduce this A to this echelon form that looks like that. And then we'll take it one step further and take it to what's called reduced row echelon form. Actually, row reduced echelon form is probably what people call it. So let's call it that. Row reduced, which makes a bit more sense, like reduced echelon form. Echelon reads stepwise, call it stepwise actually. So U is just row echelon form. Okay, so this is going to be our. Okay. So last time we talked about allowable row operations. What were they? Please remind me. What did we do with the rows when we dealt with our first examples when we solved our systems of equations?
We could multiply. Oh, sorry, go ahead.
Yeah.
Oh, I was just saying like adding rows to each other or like multiplying by scalars.
Yeah, exactly. So we could add rows. So take a multiple of that row, add it to another row, and replace that other row by the result. That's an allowed operation. We argued that it didn't change the solution set of the system. Also, if you multiply any row by a number, that didn't change the solutions of the system. If you interchange two rows, that didn't change. That makes no difference to the solution of the system. So those three were allowed operations. And we also kind of got a whiff of this, the following, that carrying out these row operations, we can reduce A to this easy looking form that kind of looked like this, from which we could like either do back substitution or even carry it further and even simplify this matrix even more and just read off the solutions from the final result. So let's do it now, just to refresh our memories that may have been quite a mouthful here. So let's see. So what am I trying to do when I do this row reduction? I want to make a 0 here, just below the first entry, the top entry, right? So how do I do that?
3 times the first row and then subtract it from the second.
Yeah, so from the second row, subtract 3 times row 1. By the way, replace row 2 with that result. So I get a 0, I get a 2 here, I get a 0 here, 16 minus 3 times 4, that's 4. 16 minus 12. So I get this as the right-hand side at this stage. Now, this guy, admittedly, we picked a very small example to begin with. We'll do a larger example later, but this guy is going to be called the pivot, this guy. Because everything below it, and okay, we only had 2 rows, so everything is just 1 0 just below it. That's a 0 below it. So that guy is going to be a pivot. This guy is also going to be a pivot. Okay, pivot. Okay, because that sits at the corner of the steps. If I make the steps like this, surrounding all these zeros underneath, so the steps are resting beneath your steps are the zeros, right? And whoever ends up at the corner of those steps, those are the pivots. Everybody else, these other guys are what's called free variables. Now, where does this terminology come from and why? Why call them free? Now, let's see if we can actually write down the solution to the system. Okay, so actually, because we're running a little short in time, let me just carry it one step further. Although I wanted to, you can already write down the solutions, but yeah.
The pivots have to be 1.
Okay, they don't have to be 1. Those are already pivot rows, but you can always make them 1. So that some people call those, refer to the pivots only when they have 1s there. But they don't have, the point is they have to be non-zero. Because why is what I said justified? Because one of those allowed operations is to divide any row by a number. So if you have any non-zero entry here, for example, here I have a 2. I can actually, let's carry out this step. I can do this allowed row operation, which is divide row 2 by 2, right? That will make all the pivots 1s. But I already called this guy a pivot here, so that's fine. But yeah, you can bring your pivot, you can make your pivots 1s. So let's actually do that.
And also, why is 2 in the first row, column 3? Why is that a free variable? How do we know?
Okay, okay, that I'm about to talk about. Okay, so the short, not the short, actually, the answer is anything that's not a pivot is free. You only have either free variables or pivots. So once you've identified pivots, the rest of the variables are free. But this will become more clear here. Okay, first of all, why did we call them free? And the answer is because we get to set their values any way that pleases us, is the answer. But we'll have a structured way of assigning values to the free variables so that we can write down the solutions to the original system nicely. But, okay, so let me rewrite this like that. And I mean, we could stop here and already write down the solutions, but let's continue the way software would do it. Usually the software, when you try to, obviously in the real world, you'll get matrices that are huge. So you can't do this by hand. So what you do is you tell the software to do exactly what we're doing right now. And the way software does it, it does what we're doing right now. And there is usually a command. Like in MATLAB, the command is ref_a. So you write down matrix A. And by the way, good suggestion. If you have a favorite software package, like maybe some of you like NumPy stack, the scientific stack in Python, NumPy does this. SciPy has a version of this. Also, it's a library in Python. The simplest is probably MATLAB is probably the simplest. If you're used to it, then it's simple. If you're not used to it, then it takes some startup time to get used to the environment. But once you're used to it, it's just a simple command. You just enter the matrix, like A, like this one. You enter this matrix and you say ref_a. Maybe I'll show it to you next time. And it gives you the following matrix. Now let's continue. I'll tell you what it gives you. It gives you this R. The command is, if you know MATLAB, it's ref_a. You enter A and then you say ref_a, and it will give you the R. So it's a good way to check your homework answers before you upload them. Anyway, let's continue. Now, we do have these pivots here. These will be pivots, I already know. And the other variables will be free. So now, to continue with this Gauss-Jordan elimination, so we're done with the Gaussian step now. Jordan comes in and says, no, you can simplify further. Just let's look at those pivots and make all those entries above the pivots zeros also. So how can I make this entry 0? So I rewrite the bottom row now, and now I'm going backward.
Multiply the second one and subtract it from the first.
Yes. And by the way, if I knew that I was going to do that, I would have done this right away here, this last computation, because 2 and 2 would just simply subtract that row there. But here now I have to multiply this by 2 and subtract it, but it's no big deal for a small matrix like this. So I get a 0 here. That looks correct. That is correct. Let's write down what we did. We subtracted from row 1 minus 2 times row 2. Again, notice that did kind of an extra step. I could have done this step there, but anyway, it is correct. So now, what does this system correspond to? What does this matrix, to what system of equations does this matrix correspond to? Don't I have like 1 times x1 plus 2 times x3 is 0. x2 plus 2x4 equals 0, right? This is the system to which we reduced the original system. How many solutions does this have? So let's explore that. So I think maybe at this point, for now, it may be easier to just look at the system itself for now. How many solutions does it have?
Can have many. So can it have?
Sorry?
Can it have like infinite?
Yes, it does have that. That's consistent with our original intuition, right? We only have a couple of, you have 4 variables and only a couple of rows, couple of constraints imposed on them. So we're going to have a lot of freedom to choose the values of those variables, loosely put. And indeed we do. Suppose we may, I think the easiest thing would be, how about let's write down one immediate solution. How about if x4 is 0, right? Then x2 can be immediately determined. What's x2 then?
0.
X2 is going to be 0, right? What's and now that I have my x4 and x2 equals 0, what's going to be the other guys? So x.
They can be something else. They don't have to be 0. x1 and x3.
They can be something else. Notice, by the way, is 0 always a solution to this?
If it's
So
equal
AX
to 0.
Yes, ax equals 0. X is always a solution. The difference from the number x equals 0 is always a solution. The difference from the usual numbers like ax equals b is that here it's the only solution. Here, with the matrices, I have non-zero solutions. Like if I set, for example, x3 equals to, let's say 1. Right, so this is 1, then x1 minus 2 equals minus 2. That's a solution, right? So that's just one way of picking out the solutions. But what we're actually going to do is we want to write that. No, that's one solution. Now you could have suggested another solution. Like for example, here's another solution. You make, say, let's make x4 minus 1. Like, I don't know why, but let's make that x4 minus 1. Then what does x2 have to be?
2.
2. And I could make, for example, x3, let's make that minus 1. I don't know why, but let's make it. Then what's x1?
2.
2 again. So that's another solution that works. And in fact, I can pick out like infinitely many such solutions. So then how do I write down the solution to the original system, this one, that I wanted to solve, that ax equals 0. That's what I was going to solve, where A is this matrix. So how am I to write this down? So let's see. What we do is we do the following. So we take our free variables. So write down, I'll show you if you've taken linear algebra before, this may not be the way you've done it, but just bear with me for a second, and then I'll write down the way you wrote it down in the linear algebra course. So my x3 and x4 are going to be free variables. What does that mean? I get to pick their values freely. My x4 and my x3. So I start picking out this value for x3, and I'm setting the other free variable to 0. When I do that, so let's work it here. Let me remove other solutions here. We don't really need them. Okay, so let's move these other solutions. Okay, other solutions away. And let's plug in x3 equals x4 equals 0. What is x2 going to be then?
0?
Yeah, 0, just from this equation, right? And once I've set x3 to 1, what is x1 going to be?
-2.
-2. That's going to be x1. Let me just stress here for a second how I've picked my free variables. These free variables are the bold-faced ones. Okay, so that's one solution. Another solution is to set my free variables like this. Give x4 a 1 and the other guy a 0. Okay, so if you know about linear independence, if you've taken linear algebra course before, and you don't have to know about this, is I'm picking out linearly independent solutions. And once I've picked out enough of them, then all linear combinations of these linearly independent, these are called special solutions, by the way. Special solutions will give me all the solutions. Special solution 1. And this, the other guy, is called the special solution 2. This one is called special solution 2. Okay, so that's the second. This one has 2 special solutions. Why does it have 2 special solutions? I'll ask you that in a second, and not say 1 or 3. Okay, but first let's actually find the second special solution. So I got to pick x4 as 1, then this x2 is then what?
-2.
-2. And what happens with x1 if my x3 is 0?
It becomes -1. Wait.
Why?
Or wait, if x3 is 0,
Yeah, x3, I've put x3 as 0 here.
then it would have to be 0.
Yeah, it's 0, right? So it's 0.
My bad.
But anyway, the point is that we wrote down the solution here. We wrote down the solution. Now, in this class, if you write down, you'll have questions like, so what's the solution to this system of homogeneous system of linear equations? You'll have questions like that. And the answer is going to be any x that is some linear combination. Let's say take C and take B. I don't know. Their sum for any C and B is going to be a solution. Why am I writing this down this way? Because I want to stress the following fact, that, again, we're viewing A's, our matrices, as linear transformations. Linear transformations we defined on day 1. We talked about something like linear transformation being a function that transforms sum into, so this linear transformation applied to the sum of vectors, for example, is the sum of the linear transformations of the original vectors. That is, here's what I said. X plus y is ax plus ay. Okay, that's not sufficient for the transformation to be linear, but it's necessary. If the transformation is linear, then this is satisfied. But anyway, here what's happened that is we found one special solution, that is a to special solution 1 was 0. A applied to special solution 2, that whole thing is also a 0. How about A applied to X special solution times 5? Is that also a 0? Right? Any multiple of the special solution. So that means if I had picked 5 here, I would have had like a different vector. We're just picking the simple special solution here by setting this free variable to 1, this free variable to 1, so on. So we had to pick something, some special. That's why I call them special solutions. Just specially pick some solution. So here it is. But any multiple of that special solution is also a solution to the original system. It satisfies AX equals B. And moreover, because each one is a solution, their sum is also a solution. Okay, so A applied to, like, I don't know, A times X special 1 plus B times X special 2 is going to be a 0. It's going to be this vector here. Some linear combination of the special solutions is going to be transported by A when A is applied to that sum to a zero vector. It's going to be squashed into a zero vector. Does that make sense? So this is a way of writing down all solutions to a homogeneous system that has many, many solutions. Now, if you've taken linear algebra before, maybe you wrote this slightly differently. So, and I just want to write it down so that, like, in this class, I accept, as long as your solution is correct, the form doesn't matter that much. So you tell me if this is the way you wrote it down. I think here's the way they told me to write it down when I was taking a linear algebra course many, many years ago. And if you didn't write it down that way, they would take away the points. So of course, I'm not going to do that. That's silly. If your solution is correct, I think that you tell me how you did this. So I think this is, you wrote it like this. So I got to this point. So let me move it here. So I think you wrote it down. So you had x1 plus 2x3, that equals 0. Then the second one says what? That x2, let me remove this. x2 plus 2x4 equals 0. And I think you just simply wrote down this x3 is simply equal x3, and x4 is simply equals x4. And the reason you write it down this way is to actually bring these guys over to this side, minus 2x. Actually, let me write it down more clearly. x4, I'm going to write down here. x3 is going to be, well, whatever it was. So first of all, this is going to be minus 2x3. This is going to be x3. So this is going to be erased. I just took that x3 on the other side, and I'm doing the same with this x4. I'm just taking it on the other to the other side so that I write it down as minus 2x4. And now the reason your linear algebra instructor may have asked you to do is here you have this vector x now. Okay, maybe written down in a strange way, but you have this vector x, which you can immediately see what the solution is. Minus 2, 0, 1, 0. This is this column. And that's why I separated the variables like that, so that I can see the multiples of x4 and multiples of x3 on the other side. Those are the free variables. Okay, is this the way you did it, people who have taken linear algebra? Or maybe not that way. Then your multiples are x3, and the other guy has a multiple of x4. And of course, the solution is the same, the way we wrote it down. And any sum, so now x3 and x4 are viewed as parameters, and you would write down the solution to this if you were given this system of equations, and were asked to solve this. At the end, you write down like this: x complete. You find these special solutions, which are these guys, and the complete solution you write down in this like this, and that was your answer. Am I correct?
Yeah, and then we would just have to say like x3, x4 element reals.
Yeah, okay. So that I'm not going to do it in this. Like in this class, I'm not going to be pedantic about this. First of all, this works for complex numbers, okay, and extensions of that field, quaternions as well. So this can be generalized quite nicely mathematically. So, but yeah, we're dealing with real numbers, and applications here, what we care about, just real numbers. So yes, again, if you forget to write down where x4 and x3 are reals, we're not taking points because of that in this class. Okay, because it's assumed that you know that. So, okay, so what else did I want to say? Now, okay, so actually we're running out of time. There are a few things that I wanted to say. I want to do more examples. So let's take this example. It will take us 2 minutes to go through. It's exactly the same as what we did, but it's just a streamlined procedure. Repeated again, okay, let's just do it. So we want to solve the system of equations. Ax equals 0. Here's my Ax. So first of all, this A is a transformation from where to where. This A is applied to what dimensional vectors? This A will take what dimensional vectors to what dimensional vectors. Okay, this is not normally like if you're asked to solve the system of linear equations, nobody asks you this question, but I'm asking people to think of this A as a transformation from some space to some space. So what is this A?
Is it a four-dimensional?
Yeah, it's applied to four-dimensional vectors and outcome three-dimensional vectors. This is the transformation A. The number of pivots in A, when you reduce it to the reduced row echelon form, is called the rank of the matrix A. And the number of the rest of the variables are free. A remarkable fact about any matrix. Well, okay, there are a few remarkable facts. The fact is that the number of linearly independent rows in any matrix is the same as the number of its linearly independent columns. If I were to do the reduced row echelon form, if I were to bring the transpose of this matrix to its reduced row echelon form, I will get exactly the same number of pivots. This is not an immediate fact. If I were, this is what I wanted to do actually, but let's take this example here. Let me, again, copy this. No, that's not what I wanted. So if I take this 2 by 4 matrix, okay, we just, okay, and if I transpose it, what does it mean to transpose it? It means just simply all those rows that we're laying down, have them stand up. So every row becomes a column. Okay, so this is the transpose of this matrix, 3, 8, 6, 16. Okay, now granted, this is a small matrix. It's 2 by 4, 4 by 2. If you do reduced row echelon form on this one, like bring this to a reduced row echelon form, you will get exactly 2 of those rows here. Well, 2 of those will be linearly independent only. So you'll have 2 pivots there. So the number of pivots in A or A transpose is exactly the same. In this case, it's 2. We'll talk more about ranks later. But that's one observation. Actually, we should be talking a little bit more about that. That's one observation to keep in mind, and we should talk about that more. But let's go through this concrete example one more time before we leave, and then talk a little bit about inverse matrices and talk much more about them next time. So you do the usual Gaussian elimination in this. What does that mean? To bring this first to a matrix that we call U. This is the U matrix. That's the echelon form. Okay, so subtract twice row 1 from the second row. It makes a 0 here. So you get the idea. So that's what the matrix is. Then you do the same. You try to make a 0 instead of this 3. How do I make a 0 there? Well, you from row 3, from this guy, subtract 3 times the first row. That would make this 0 here. You do the same with the other entries. You get this row. And now notice what happens. What happens here is that the third row and the second row are exactly the same. So when you do this elimination one more time, that is, try to, now this is your pivot. Yeah, it's -1, but you can always multiply the whole row by -1 to make this a 1. So let's call this a pivot. It's a non-zero entry. So to make a 0 below it, okay, you just simply just subtract this row from this row to put a 0 in, but that puts 0 everywhere else. So what does that mean? In this case, I have 2 pivots again, and 2 free variables. Okay. Now, what is the solution says? How many solutions will I have? What's the solution? When we wrote down the solution here, it was exactly the same setup here. What does this geometrically look like? So first of all, we're dealing with a 4-dimensional space, right? We can't really be honest with ourselves and say that we're imagining this, right? But in a 4-dimensional space, what kind of structure is that? This is some vector. This is another vector. And I'm taking, so that we can actually draw somehow. So here's one vector, V1, that's special solution 1. And this is another vector, V2. Now I drew them on the plane. We can easily imagine them in 3 dimensions, like in the room. We can't imagine it in 4 dimensions. But we can imagine what vectors are these guys if we have the first 2. So what does this say? Is it the plane that's formed, spanned? It's called spanned by those 2 vectors. So for example, how do you get a vector like this? You take some amount of V2, maybe 3/5 of V2, and add maybe like, I don't know, 11/10 of V1, whatever. You add these 2 up somehow. Okay, so this red vector turns out to be like roughly V1 plus 3/5 of V2. Is that, let's call this vector U. any vector that lies on the plane can be some linear combination. This is called the linear combination of v1 and v2, which just simply means some number times v1 plus some other number times v2. Okay, so for example, this vector is minus v2 plus v1, minus 2 times. So this vector, let's go with the purple. So this vector here is going to be minus 2 times minus 2 v2 plus v1 again. I don't know why I selected this example again, but you get the idea. So this w vector. This w vector may be minus 2 v1 plus v2, and so on. Anything on that plane can be expressed as some linear combination of those two vectors. This solution forms a plane in a 4-dimensional space, a plane that is generated by those two vectors that are the special solutions. What this system of linear equations tells me is that that plane, it's also called a singularity. Why is it called a singularity? Because the entire plane, as a result of applying A to anything in that plane, any vector in that plane, is crushed into a zero, into a single point. It's called a singularity. It's the solution. So the entire plane, as a result of applying A to any vector in it, is crushed to zero. That goes to zero. A of everything here is a zero, right? Okay, we'll talk more about that later. Okay, so I think we're running out of time. So I'll see if I can record another section and try to get more done there, because I also want to talk about inverse matrices. But I'll talk about inverse matrices next time, so that's no big deal. Okay, so we're not, if you've taken linear algebra and you have this formula, like how to compute the inverses and so on, so forth, let's forget about that for now. Okay, we'll think of inverse of a linear transformation as an undo operation. We have 4 minutes, so why not talk about this for a second? So where are my slides with? So here's a linear transformation, the matrix that we've always been writing down: 1, 2, 3, 4. The simplest that it's not the simplest we can think of, but a simple matrix. Now I want to compute its inverse. What does it even mean to compute an inverse? Well, we said it's a linear transformation. It's a 2 by 2 matrix. It's applied to 2-dimensional vectors. Okay, when A is applied to 2-dimensional vectors, so A is applied to stuff here. Okay, and this is the result. A x's are there. All the b's are there. So for example, when I take this A, this is input space on the left and output space on the right. When I take the red vector here, 1, 1, and when I apply, this is my A. When I apply A to 1, 1, then out comes this vector 3, 7. I can plot that vector. Here it is. This is A times 1, 1. I can take the blue vector, 1, minus 1, and that comes to this vector, 1, 1, when I apply A to it in the output space. And you can do it with a bunch of vectors. You can, let's say, the green vector, 1, minus 2, this vector. When I apply A to it, this is the vector that comes out on the other side. So some linear transformation, no big deal. But what does it mean to invert this linear transformation? It means that once you're now the input space is this, R2, then can I find some transformation? You may want to call it B, but there's a special notation with this. It's just denoted by A to the minus first. It's called the inverse operation. It's just some matrix. Actually, for now, let's just call it B. Is there a matrix B? And what does that be? When B is applied to the vectors in this space now, can I recover the original vectors in the original space to which A was applied so that I would get the vectors here? So for example, vector B, if I applied it to the blue vector, would I get the original blue vector in the original space back? If I find such B that takes every vector here to their original vector, then we'll call that an inverse. This is a very loose way of putting what an inverse is. It's an undo operation. But does it make sense, right? So I have some linear transformation. It brings these vectors to these vectors. And the question I'm asking is there a linear operation to which I can apply to these vectors now so that I get back the original vectors back in such a way that this red vector is taken here, the green vector is taken here, and the blue vector is taken here. And let's find a way of finding such transformations. And it turns out there is, for this particular A, there is. Now, the fact that there is a formula computing this with determinants is true, but where does it come from? Okay, how exactly does it do the undo operation, the strange formula that has 1 over determinant, and then here you have the, you changed A in such a way. In the 2 by 2 case, there's a simple formula, and 3 by 3 case. But it gets more complicated and computationally expensive to do it for n by n matrices using those determinants to compute. Okay, so this is where we end.